Okay, so we talked about how you can determine the empirical formula for a compound. You need the masses of the elements that are present. And how do we get those masses? For organic compounds, those containing carbon, hydrogen, and oxygen only, a common technique is combustion analysis. And so you take the compound, you weigh it, you put it in a furnace, and you burn it. And then the products of that combustion are carbon dioxide and water. All of the carbon forms carbon dioxide and can be collected and measured. All the hydrogen forms water. You collect that and measure it. And then if the compound had oxygen in it, we find that by subtraction. So you've got the mass of carbon, you've got the mass of hydrogen, you've got the original mass of the compound, and so you subtract and you find out what's missing. That must be the oxygen. So this is a sketch of an apparatus to do combustion analysis. You've got a furnace in here, you've got the compound, you stick it in here, and you've got oxygen flowing in because oxygen is necessary for combustion. You heat it to ignite it, and it burns. All of the gases given off come out and go through these tubes. So in this first tube is a substance that absorbs water. So before the analysis begins, you take this tube and you weigh it. The combustion occurs. The water given off from the combustion goes through this tube and gets stuck in the tube, absorbed. That causes the tube to weigh more. So when you weigh the tube afterwards, the increase in mass is due to the water that came off of the combustion of that sample. After it goes through that tube, it goes through a carbon dioxide absorbing tube that catches all the carbon dioxide, and then anything that's not carbon dioxide or water would get just come out the other end. So we can get the mass of CO2, the mass of water. We're pumping oxygen in here, right? So the oxygen in the water and the CO2 probably didn't come from the compound itself. Probably came from the oxygen that we were pumping in. So this is something you probably didn't hear about in Chem 3A. What it really is a couple of different things put together. Each of the individual pieces is not hard, but it can be tricky to remember where you're going. You can get lost in the forest, right? So there's a lot of little pieces here. Now, I'll also tell you, you can pass the class without being able to do a combustion analysis problem. But I still think you should give it a try, right? You should always try. So here's the question. Upon combustion, a compound containing only carbon and hydrogen produce 1.60 grams of carbon dioxide and 0.819 grams of water. Find the empirical formula of the compound. So we're given masses of these two compounds. This CO2 has all of the carbon. So what we have to do is we have to take this mass of CO2 and find out how much carbon is in it. And we need to take the mass of water and find out how much hydrogen is in it. Sometimes when you're doing a problem like this, it's actually helpful to write out the steps to remind yourself, because when you get in the middle of calculating, it can get lost. You get caught up in the calculating, and you might calculate things that you don't actually need. So the first thing we're going to do is take the mass of CO2 and find out the amount of carbon. So we have grams of CO2. So we learned how to do this, find the mass of an element when we have the mass of the compound. So we need to convert this to moles. And so in the bottom is grams of CO2. So the mass of carbon, 12.01, plus 2 times the mass of oxygen gives us 44.01 as the molar mass for carbon dioxide. So that gives us moles of CO2. From the chemical formula, we can get moles of carbon. CO2, in one CO2, how many carbons? 1. So there's 1 mole of carbon in 1 mole of CO2. So looking at my units, I would be at moles of carbon. So in calculating an empirical formula, you take the mass of the element and you convert it to moles of the element. So here, I could take this moles of carbon and convert it to mass so that I'm starting at the same place and then convert it right back to moles. Or I could say, oh, well, this is what I need. So I'm just going to stop here. So this is what we want. We want moles of the elements. So 1.6 divided by 44.01 times 1. So this is 0.036 355 moles of carbon. Again, don't round too much. Always better to use too many digits. Then I'm going to take the mass of water, 0.819 grams of water, and I'm going to do the same process. I'm going to convert it to moles, and then moles of the element. So moles of water, and grams, water, and grams of water down there. So you have to calculate the mass of, molar mass of water, 18.016. And then I'm going to convert from moles of water to moles of hydrogen. So in one H2O molecule, how many hydrogen atoms are there? There's 2. So in a mole of molecules, there are 2 moles of atoms. So this is 2 to 1. So this ratio here is coming directly from the chemical equation. Here there's 2 hydrogens in this, so it's 2 to 1. There is 1 carbon in CO2, so it's 1 mole of carbon per 1 mole of CO2. .819 divided by 18.016 times 2. So this is 0.0090919 moles of hydrogen. So what do I do once I get my moles of elements? I need the ratio, right? So I need the ratio of moles in small whole numbers. Well, I've got yucky fractions. I'm going to take the smallest and divide both of them by the smallest. So this one gets divided by itself. And that's going to be 1. And this one gets divided. And I get 2.5. 0.008. So that's definitely 2.5. Is 2.5 a whole number? No. Can I round it to 3? No. It's exactly between 2 and 3. So this is 2.5. So I want to multiply both of the numbers so I get a whole number. So if I multiply this times 2, I'm going to get 5. And if I do that to one, I have to do it to the other, and so this one becomes 2. You want to keep the ratio the same. So this tells me I've got C2, H5. Any questions? From this point where you have moles of each element, the rest of it is just like the regular finding an empirical formula. Yeah.
So in that case, it was only carbon and hydrogen.
Right.
So we be able to find mass of oxygen.
I'm so glad you asked, because that's the next example. So here we've got a compound with carbon, hydrogen, and oxygen, because this adds another layer to the problem. Upon combustion, a 0.8009 gram sample of a compound containing only carbon, hydrogen, and oxygen produces 1.6004 grams of CO2 and 0.6551 grams of H2O. Find the empirical formula. So we're going to do very similar thing. We take the mass of CO2, find moles of carbon. From the mass of water, find the moles of hydrogen. But to find the oxygen, we're going to have to subtract, because that can't be measured directly. So let's just start and figure it out as we go along. So 1.6004 grams of CO2. I'm going to convert that to moles of CO2. And the molar mass is 44.01 grams. Because I do this so many times that I just remember it. Then we want moles of carbon in moles of CO2, and it's 1:1. So this is the same as the previous problem. This one has 5 sig figs, and so I'm just going to round this to 5 sig figs. 36364 moles of carbon. And then I do the same idea to hydrogen. 0.6551 grams of hydrogen. Of water. I convert to moles of water. And then to moles of hydrogen. Oops. It can be tempting to leave off that mole ratio. I would encourage you to not do that. For the CO2, it doesn't matter. It's 1:1. But for the water, it does matter. And if you forget that, then your answer is going to be wrong. So those cancel, and those cancel. 0.6551 divided by 18.016 times 2. So this is giving me 0.07272 moles of hydrogen. There is also oxygen. I can't take the mass of the compound and convert to moles and then subtract the moles of carbon and hydrogen, because I don't know what the compound is, because that's what I'm trying to find, right? So we have to do the oxygen by masses. So even though moles of carbon and moles of hydrogen are what we ultimately want to find the ratios, I also need the grams so that I can find the grams of oxygen. So I'm going to go to a different color here. We're going to keep those numbers right there. That's why I wrote them down. But then we also have to convert to grams. Grams of carbon to moles of carbon. So that's 12.01. So 0.43674 grams of carbon. And for hydrogen, we've got grams of hydrogen to moles of hydrogen, 1.008 grams for every mole. Any questions yet? I found moles of carbon and moles of hydrogen because I need those to find the empirical formula. I'm taking it one step further and finding mass of carbon and mass of hydrogen because I need to find the mass of oxygen, and I have to do that by subtraction. So the entire compound weighed 0.8009 grams. 0.43674 of that was carbon, 0.07331 of that was hydrogen, the rest was oxygen. Okay. So I'm going to take the mass of the compound, 0.8009 grams compound, and I'm going to subtract the 43674 grams of carbon, and I'm going to subtract 0.07331 grams of hydrogen. Use your calculator, don't do that the long way. So 0.8009 minus 0.43674 minus 0.07331 equals 0.29085 grams of oxygen. I can't do that really any other way because the oxygen and the CO2 in the water came from the oxygen that we were pumping in to the furnace so that it would burn. So there's mass of oxygen. I've got moles of carbon that I saved up here and moles of hydrogen. I need moles of oxygen. So there's grams of oxygen to moles of oxygen. 1 mole is 16.00 grams. So I take that number and divide by 16. Here's my moles of oxygen. I took that out to 5 sig figs because I didn't feel like rounding the 7 up to an 8, and when I got to the 8, I realized I didn't have to round it up or down. It's more than is needed, yes.
Would the sig figs be dependent on their subtraction?
Yes. So in this subtraction here, the original number had 4 decimal places, and so when I subtract here, I get 4 decimal places. And so that's the last significant figure. We're going to end up with whole numbers, right? So the key here is to keep enough digits. If we round too much, if I round this to 0.02, I'm going to end up with the wrong fraction. If I keep the minimum number or I keep more, I'm going to be okay. So I just wrote 1 extra there because I felt like it. Do you want me to make it just right? The right number? Yeah, okay. Okay, so we've got moles, whoops, and a purple line. I've got moles of carbon, moles of hydrogen, moles of oxygen. I need to divide by the smallest. Now be careful, because these numbers that are much less than 1 can get a little confusing sometimes. Which one is the smallest number of moles? The oxygen. So this one's divided by itself. That is 1. And this one is divided by the same number. So 0.07272 divided by 0.018178. What I'm doing here is not really looking at significant figures. I've got 4.00. I'm just going and I'm going to go until I find the first non-zero digit, just to show you that this is really close to 4. So this is going to be 4. And then this one, 0.036364. Oh yeah, that's not good. I use the minus sign instead of 0.36364. And so this is giving me 2.0004. So that can be rounded to 2. This can be rounded to 4. And the other one's a 1. Right? So I don't have to multiply all of the ratios. I can just write them down. Now, they presented you with carbon, hydrogen, and oxygen in that order. That's the order they're going to show it to you in the answer. So carbon 2, hydrogen 4, oxygen 1, except we usually don't write the 1. C2H4O. Empirical formula. Any questions? With an organic compound, that's probably not the molecular formula, but then you need to do another experiment, such as mass spectrometry, to find the actual molar mass of the compound, and then you can find the empirical formula. I'm sorry, the molecular formula. So, any questions?